Hello fellow problem solvers. So today we're going to be doing a problem from the Canada Mathematical Olympiad 2021, problem number 4. I suggest you try this problem out for a minimum of 20 minutes, ideally an hour to an hour and 20 minutes, but not more than 2.5 hours. If, on the other hand, you would like to go along with us, I suggest you take 10 minutes, plug in some stuff, get your first ideas out on paper. And now, let's begin. So, in summary, we have a function from the positive integers to the positive integers, and the condition that for every x and y in the positive integers, we have the GCD of f of x and f of x plus y is equal to the GCD of x and y. Our goal, we call a function which satisfies this Canadian, and our goal is to find all m such that if f is a Canadian function, then f of m is equal to m. So now, the first step really is to play around with some values of x and y, plug them in, and see what f needs to satisfy. And here I invite you, if you haven't already plugged in a couple of values that you find interesting, I invite you to do that just now for the next 5 to 10 minutes. Okay, with plugging in, the first thing I sort of plugged in was y is 1, or x is 1. Because what I get for, say, y is 1, I get the GCD of f of x and f of x plus 1 is equal to 1. Okay. I don't know if this is useful or not, but I'm just plugging stuff in and seeing what I get. If I plug in x equals 1, then what I'll get is f of 1 constant and f of y plus 1 is equal to 1. And right now I see this severely restricts the function. This means that f of anything greater than 1 and f of 1 is going to be 1. So maybe I could maybe find an argument to prove that this needs to be 1 in that case, but let's do that a bit later. Let's find that out later. Let's plug other stuff in. So the next sort of thing is plug in x equals y, and then what we get is that the GCD of f of x and f of 2x is equal to x. So what this right here implies is that x divides f of x, and it divides f of 2x. Now this is interesting. This tells us that f of x is equal to x times some k of x for each x, where k can be different for now. And okay, let's move on. So we have this on one side. We have x dividing f of x and f of 2x. We can also plug in y equals kx, and what we will get is that the GCD of f of x and f of k plus 1x is equal to x, which means x divides f of kx for each k greater than or equal to 2. Okay, so now we have that as well. Let's see, we have x dividing f of x because we got x out here, basically. Can we get f of x or something similar out here so that we can have some equality, actually? And to do that, the easiest way for me is to plug in x plus y equals f of x. Now the problem with this is we can't really plug this in because this would mean y is f of x minus x, and if x is greater than or equal to f of x, then we have a problem because we're in the positive integers. And now maybe this is a good chance for you to pause for another 5 to 10 minutes and play around a bit, try out some ideas. So here's the next thought. I can't really have this, right? So could I have something else, something maybe divisible by f of x? Now the question is, what does f of x divide? Well, from here, just plugging in x equals f of x, like plugging this into this, we'll get this divides f of k times f of x for each k greater than or equal to 2. Now, can I make x plus y equal k times f of x for some k? And the answer is definitely, because then y is equal to k f of x minus x, and if we choose a big enough k, we are definitely in the clear because this is a constant and k is free floating. It can go till infinity, as big as we want it to get. Though also, truth be told, we don't really need this because from x dividing f of x, we know x is less than or equal to f of x, so k equals 2 is good enough. Either way, I'll just plug in this, and what we'll get is that f of x is equal to the GCD of f of x times f of k f of x and this is equal to the GCD of x and k f of x minus x. Now from here, because this is equal to the GCD of x and something, this means that this divides x, so f of x divides x. And now what we get from here, and from the fact that f of x divides f of x, we get that this implies that x is equal to f of x. And now our Canadian function problem condition translates into the GCD of x and f of x plus y is equal to the GCD of x and y for all x and y, with the extra condition that f of x is equal to x. Now with this, I invite you to pause for another 10 to 20 minutes and see how far you can push this. Can you find f of x in general? Or can you just solve the problem, do the easier task, which is find all m, such that for all Canadian functions, meaning all f's which satisfy this for every x and y, that we have f of m is equal to m. Can you find all such m? Now I will give you at least 10 to 20 minutes to work on this. Here's the next step. So this is our function. The f of x is x, and GCD of x and f of x plus y is equal to the GCD of x and y, which is equal to the GCD of x and x plus y. And the reason I write it like this is because look at f. The only things we'll be able to put in here now is any number which is greater than x. That's what the function is right now. So we can just rewrite it as the GCD of x and f of t is x plus y, and equaling the GCD of x and t, where t is greater than x and both are positive integers. Now for me, I thought I could find f, that this was enough for me to figure out what f is. And even more naively, I thought that the only answer was f of x is equal to x. That is the only solution. And that's where I got wrong, because if f of x, like this is just a way to think about problems that come on competitions, is that if f of x equals to x is the only solution, the problem would not be find all m, such that for every f of m is equal to m. The problem statement would be find all functions which satisfy this thing. So that's maybe a little cheat code, so to speak, on how to think about problems that you get on these competitions. So now, a way to maybe test that hypothesis would have been, what if f of 1 is equal to some c that's greater than 1? Well, that implies that f of c is equal to 1, so when I plug in c as t, I'll get the GCD of x and 1, which is 1, is equal to the GCD of x and c for all x less than c. And now this actually can be true if c is a prime number. And now you can see maybe that if c is prime, then putting t as c, this is the only place where we have an f. For t is equal to c, which is a prime, we will have the GCD of x and that prime, which is 1, equal to the GCD of x and prime, which is also 1 for all x less than that prime, so we'll be good. And if f of x is equal to x for every single letter x, that will be a solution. And now with that, we know that m is not equal to any prime number or 1. And I also realized something that I've been doing here implicitly is, instead of finding all f's such that we have whatever the f of m is going to be equal to m, I'm trying to find f's and f such that f of m isn't equal to m for some m. And if I can find all m's such that there exists an f for which f of m isn't equal to m, then I know all the m's which have f of m is m for every single f. And I just wanted to mention that because it's something I implicitly did intuitively without saying why. I mean, the reason why is because it's easier to construct f's than it is to find all these m's at the beginning, because like I was thinking that f of x equals x is the only solution, but in fact it's not. So now let's explore other types of t. So we have x and f of t and x and t. Let's say what if t is a prime power, p squared, f of p squared, and x is equal to x and p squared, the GCD. Well, we need that for x equals prime, or p times k, for any k less than p, we must have f of this is going to be equal to p. Okay, so the f of this prime power must only have p's in it. It can't have anything that has a divisor less than p. It can be p times some other prime, but let's think simply. What else can it be? What if it's just f of p squared is p, and then this implies, because of f of x is x, this implies f of p is p squared. Does this satisfy our problem? Well, for this part it does. And for this part, I invite you to pause for another 5 minutes and figure out if it does. And now that you've hopefully paused, for this thing, we will have some x less than p, and f of p is p squared, is equal to GCD of x and p, where x is less than p. This is always 1, this is 1, so we are good. And now we can see that m isn't equal to 1, p, and p squared. Because if we just plug this in for some prime and make all the other x's equal to x, we are done. And by we are done, I mean we have a function such that f of p squared isn't equal to p squared, and which satisfies the problem conditions entirely. So now let's maybe look at p cubed, and then we can look at p times q. So for p cubed, we have x, and f of p cubed is equal to f of x and p cubed for all less than p cubed. And now what this means for x equals pk, where p does not divide k, and k is less than p squared, this means that f of pk and f of p cubed is equal to p. Okay, and if we plug in, say, p squared, x equals p squared k, k less than p, now what we have is kp squared, f of p cubed is equal to p squared. Okay, so now we know that f of p cubed needs to be divisible by p squared. Now, what if we just make this equal to p squared, and by implication, f of p squared is p cubed? Does this solve our problem? And the answer is, well, this obviously solves our problem given what we've figured out. If you plug in x not divisible by p, you'll just get 1 on both sides, which is good. But does this solve our problem for all p squared? Okay, so if f of p squared is equal to p cubed, what does that give us? It gives us f of x and p squared, f of x and p cubed equals x and p squared for all x less than p squared. And this is true. And it's true because none of these x's are divisible by p cubed because they're less than p squared, so this thing holds out. And now maybe you can see that inductively, actually, I'm not going to tell you what you can see. I invite you to pause for 5 to 10 minutes and figure out what you see. What other values, so 1p, p squared, p cubed, m can't be any one of those for prime number p. Are there any other values that m cannot be? Take 10 minutes now. And here's the answer to that. So if we plug in f of p of alpha is equal to p of alpha plus 1, f of p of alpha plus 1 is equal to p of alpha, and f of x is equal to x for all other x, and this satisfies f of x is equal to x for every single x. And does it satisfy this for each x less than t? And the answer is it does. In the first case, if t is equal to p to the alpha, then this must be satisfied, which is true, because this is all going to be less than or equal to p to the alpha. This is never going to be. X is less than p to the alpha plus 1, so this is true. And this is true by the same argument, and this is true because it's identical. So now we know that m equaling 1 or p to the alpha for some alpha does not work. Now, what about m equaling p times q, where p and q are different prime numbers? Well, let's see. We have x and f of p times q is equal to x and p times q for all x less than p times q. Well, okay, let's see if this is true. So for x equaling p, we have that p and f of p times q, that this is equal to p. So that means p divides f of p times q. And for x equals q, this means that q and f of p times q is equal to q, which means that q divides f of p times q. Oh, and because these are different primes, that means that p times q divides f of p times q. And now, well, this is a bit different than what we had up here, because here we use the fact that this number doesn't need to divide the f of that number. But here we have p times q divides f of p times q. And the main reason we could do this is because p and q are relatively prime to each other. And that's because if a divides c and b divides c, and the GCD of a and b is 1, then a times b divides c. Now immediately what I'm thinking is this specific to these p times q? Now this is p times q times something else. Does this number also divide its f? Because if it does, then this number divides its f, which is f of p times q, which is equal to pq. And then we'll have pq is equal to p times q. So with this in mind, I invite you to take 10 to 30 minutes and try to finish the problem up. And here's the next step. Namely, let this number m be equal to a times b, where both a and b are greater than 1, and their GCD is equal to 1. If m is not a prime power, we can do this. So let m be this. Now, plugging in x equals a, and t equals a times b, and then x equals b, and t equals a times b, what we have is that GCD of, and also every time I wrote these brackets, I just meant the GCD. It's a shorthand. The GCD of a and f of a times b is equal to a, and the GCD of b and f of a times b is equal to b. And this implies that a times b divides f of a times b. And it's implied from the fact that a divides f of ab, b divides f of ab, and because a and b have a GCD 1, that implies that a times b divides f of a times b. Now with this, we know that for each m that's not a prime power, we have m divides f of m. But then f of m is also not a prime power because it's divisible by a number which is not a prime power. And then this divides f of m, and now this is equal to m. And now from m divides f of m, which divides m, we have f of m must be equal to m for all such m. And this really solves our problem. This finds all m such that for every Canadian function, we have f of m is equal to m. Namely, it's all the m's which are not equal to 1, or p to the alpha for some prime p. And now I invite you to take 10 minutes and write up a solution. Here's our solution. So firstly, we define p of xy as the thing that implies the GCD of f of x and f of x plus y is equal to the GCD of x and y. And now we plug in a bunch of things. And what we get is that p of x and x, we get x divides f of x, and x divides f of 2x. And from the one, we know that f of 2f of x minus x is greater than or equal to f of x, which is greater than 0. So we can plug that in as y, and we get that f of x divides x as 4. And now we say, from 1 and 4, x divides f of x divides x, so x is f of x. So p of xy is actually the GCD of x, and f of x plus y equals the GCD of x and y. Now, what we say is, a function for which f of x is x, and the GCD of x and f of t is equal to the GCD of x and t for all x less than t and both natural numbers, we have that kind of function is a Canadian function. So now we prove that any m, which is not a prime power, we have f of m is equal to m. And the way we do this is by first proving lemma 1, namely if m is not a prime power, or 1, then m divides f of m. And the way we do this is say let m equal to a times b, where a and b are greater than 1, and their GCD is 1. Then for x equals a, and t is equal to a times b, and x equals b, and t is equal to a times b, we have the GCD of a and f of m is equal to a, GCD of b and f of m is b, and that implies a divides f of a times b, b divides f of a times b, and because a and b are relatively prime, this implies a times b divides f of a times b, i.e. m divides f of m. And now with that, we say that if m isn't equal to a prime power, that implies that m divides f of m, which implies f of m isn't equal to a prime power, which then implies f of m divides f of m, which is equal to m. And from here, we have m is equal to f of m for all such m. And now we move on to the last part of the proof, namely that there exists a Canadian f such that f of p to the alpha isn't equal to p to the alpha for all primes p and all alpha that are non-negative integers. And we prove this via construction, namely, we show that this function is indeed Canadian. It's an involution, so the only thing we need to prove is that the GCD of x and f of t is equal to the GCD of x and t for all x less than t. If x is equal to p to the alpha, this implies that the GCD of x and p to the alpha plus 1 is equal to this, which is true because x is less than p to the alpha. And the other two imply that GCD of x and p to the alpha is the GCD of x and p to the alpha plus 1 for all x less than p to the alpha plus 1. This is also correct because x is less than p to the alpha plus 1. And finally, that this also holds, which is true because it's an identity. Now this solves the problem. This means that all m which are not prime powers or 1. And as always, thanks for problem solving.